Hi everyone, I'm really happy to be here giving this talk today. My name is Jenna Samuel, I'm a postdoc at UT Austin, and I run and use the fire simulations to study galaxy formation. That was, up until very recently, only confined to the local group, and now I'm a high redshift person, I guess. So hopefully I'm a decent person to give you this talk about connecting substructure in the local group to high redshift galaxies. I'm going to focus on basically two topics, or at least one, which is the UV luminosity function, and kind of using that near-far technique to get a handle on the faint end of the UV luminosity function at high redshift. So this is a pretty common plot that you've probably seen before, the UV luminosity function at redshift of about 7 from Mike Boyle and Colchin's 2015 paper. It's slightly outdated now, so I've added a little note up here, or another annotation, but basically what this is showing you is that even with JWST, in the absence of lensing, you get down to about the luminosity of the LMC, so the most massive dwarf galaxy around the Milky Way at a redshift of 7, and we think that things that were very faint were responsible for reionizing the universe. So if you use JWST plus lensing, like Keem's program Glimpse, you will get down much further than this. However, that will only get you down to about luminosity of Fornax or Sagittarius, and you're still missing a ton of the very faint galaxies. So the fact that we have a good amount of overlap, or we will once we get those Glimpse results in, we have a way to sort of test the near-far approach for measuring the UV luminosity function in the regime where there is overlap, and hopefully validate the near-far approach to study the UV luminosity function at magnitudes that are fainter than what JWST will ever be able to see. And so why should we care about magnitudes that are fainter than what JWST will be able to see? So this is some recent work by Andre, and I believe his student, showing that using his semi-analytical model, the reionization history of the local group is consistent with reionization around redshift of 8.5. And if you look at the fraction of ionizing radiation contributed as a function of the different of the UV magnitude here, if you're looking at that redshift, or above it, purple, blue, and gray here, you're getting a really significant contribution from galaxies that are fainter than the JWST plus lensing detection limit. So we should care about these very faint galaxies and trying to use the near-far approach to look even fainter than JWST will get us. Oop. So I'm using the word near-far approach, and we've talked about it a little bit, and some people will also call this the fossil record approach, and Keith kind of explained this a little bit in terms of looking at the Milky Way's merger history, but I just wanted to kind of review it because I know not everybody is super familiar with what the fossil record here means. So basically, we start on the right-hand side here, right? You can observe or simulate a bunch of low-mass galaxies in the local group. And you can measure their stellar mass function or their UV luminosity function, right? If you have resolved stars, you can also measure or back out their star formation history, right? And so then you know how massive that galaxy that has survived to redshift 0 was at previous points in the past. So you can build archaeologically a stellar mass function in the past. However, the population of galaxies that survives to redshift 0, right, that's not the full population of galaxies that existed at higher redshift. That was Keith's point. A lot of those merge in to form the Milky Way. Some of them merge with each other. And so the UV luminosity function or stellar mass function that you end up backing out, how do we know that we can actually trust that? And I know a lot of people are skeptical about this, so I'm here to kind of convince you that maybe this isn't possible right now, but it's going to be, okay? And so one of the really promising reasons why this is going to be possible is from some nice work that got dropped on the archive a couple weeks ago by Yuan Ting and Alex G, who we heard from earlier today, showing that, this is our old method for getting star formation histories for these low mass galaxies in the local group from color magnitude diagrams, where we got maybe 1 or 2 star formation bins per gigayear. Now what you can actually do is use the alpha element tracks of these galaxies to back out star formation histories on timescales as short as 100 million years. And so basically the idea behind this, and Alex is the expert here, I'm not going to try to explain it in detail, is that instead of just assuming, oh, we see this kind of track, the dashed yellow line here and the alpha versus iron plot, there's actually substructure along that track, and you can use Gaussian mixture models to pick out those structures that correspond to bursts in star formation. There's some additional criteria that you need, but basically you could get from this blue line model for Sculptor here to this really nicely time-resolved star formation history plot, rather than what was sort of the state of the art in the past. So this should give us confidence that at least in the near term, it will be possible to get actual time-resolved star formation histories of low-mass galaxies and local group during the reionization era. Okay, so you could measure the star formation history, but how do you know that what you are inferring from the surviving population is representative of what was going on at high redshift? And so this is where the role of simulations really come in, right? Because we can do both the bottom and the simulations. We could try and reconstruct the star formation history of surviving galaxies, and we can also look at all of the things that have merged into the Milky Way, so all the things that don't survive all the way down to redshift 0, and see how much we're recovering of the high redshift population just from the surviving population. And we can also just go back in time in the simulations and measure a high redshift stellar mass function, UV luminosity function as well. And so this is not work that I've worked on personally, but rather this is something that grad student and soon-to-be postdoc at Yale this fall, Pratik Gandhi, has been working on. So he's already published some work showing that this is feasible in terms of the stellar mass function, and right now I'm showing you some in-prep work from him showing you that this is also feasible for the UV luminosity function. So what you're looking at here as the UV luminosity function for just the dwarf galaxies in the local group, the fossil record, so what you can recover from this fossil record method by looking at the star formation histories of survivors is what you get in blue, versus if you just look back at redshift 7 at what the UV luminosity function looks like then, you get that pink line instead. And they do not line up with each other. You had more things. You had more small galaxies in the past. That's to be expected. But the convenient or nice part of this is that they're offset by about the same amount as a function of MUV here. So it's basically a simple kind of normalization factor that can get you back to this. And so Pratik has also shown that this is the case, as you would expect, for the stellar mass function as well. It's relatively insensitive to stellar mass and UV luminosity. So we can get the we can get the high redshift UV luminosity function in the local group from the fossil record. Now the question is that UV luminosity function representative of the global UV luminosity function, right? Because that's what we're interested in, what reionizes the universe in general, not necessarily just the local group, right? And so this is where my work is coming in. And so this is all very preliminary in the past few days, basically. But I have this large volume run with Fire 3 models. I'm calling this simulation Bonfire. And you can see this is a little bit over half the volume of TNG 50. I've only got a low resolution version so far, but that's still pretty good resolution in terms of a large volume galaxy formation simulation. We can talk about the details of Fire 3 updates later, but the net effect is that we have better cooling and star formation prescriptions in the early universe where we're interested in looking at these things. And why do we need a large box to do this? Well, what we want to do is we want to see what the global UV luminosity function is inside of the box, and then see whether or not, if we can pick out proto-local group volumes, does that UV luminosity function at the faint end represent the global UV luminosity function. And so here's what the global UV luminosity function looks like. So, I mean, like a key prediction just from the global itself is that there isn't a turnover, where we're going to be sort of looking for that turnover with JWST plus lensing. There's a bump instead, and that's because we have a lot of clustered star formation. We can, as a whole other talk, and we can argue about that later. But there's no turnover until you hit basically like really bottoming out on the resolution limit of this simulation. All right, and then if we select a bunch of proto-local group volumes just according to these criteria, and again, this is kind of a first pass in terms of these criteria, but it's pretty consistent with the mass growth histories in zoom-in simulations and in semi-analytical models. We can then get the UV luminosity function in those proto-local group volumes. There's like 200 of them in the simulation at redshift 8. And you can see that they line up pretty nicely at the faint end, and they start to peel away. So at the faint end, the local group is pretty representative in general in terms of the global UV luminosity function. But you know, the local group is not one of the more dense. It's not one of the densest places in the universe. So we start to peel away from the global UV luminosity function brighter than magnitude of like -13 or so. And this is pretty consistent with some estimates that Mike had made earlier, basically using abundance matching and dark matter only simulations of the local group in the past. It peels off right around the same area, around -14. Okay, so it's pretty convincing to me, at least, that we are safe to use the fossil record UV luminosity function in the local group to at least look at the very faintest ends of the global UV luminosity function. And ideally, maybe it's worth arguing, there's hopefully enough of an overlap here to sort of validate or fact check with direct high redshift observations with JWST. How am I doing on time? Okay. So the rest of it's mostly just pictures, so I'm not going to say too much anyway. But I wanted to show you, I mean, we've already seen this beautiful picture of the firefly sparkle, so a Milky Way progenitor that seems to have some very recent bursts in its star formation history corresponding to these nice compact clusters. And so my point here was just, you know, the things that I'm selecting as Milky Way progenitors in the local, in Bonfire have some pretty diverse morphologies. This is all at redshift 8 within the stellar mass range that I was selecting on. You know, this one looks kind of a firefly sparkle-like, but you even have things that are like a single cluster here, right? And I just want to point out that they have some similar star formation histories where we're really starting to have a large boom in star formation right at the end of the simulation, right at around 650 million years after the Big Bang or so. So kind of similar to what's being seen for a firefly sparkle. And this is super early days, so all I have are these images right now, but the idea here is that we can also use these sort of proto-globular clusters to try and address sort of the formation of the Milky Way itself from disrupted globular clusters and look at their fate. Probably not in Bonfire itself, but maybe in future zoom-in simulations that we run on these regions. Okay, and so I'll just leave you with the summary there. Thanks.
Thank you.
Thank you for nice talk. And so, could you go back to the last slide? And so, this looks very much like firefly. So observed one, and so those clumps are during the merger, or so formed inside the same halo, or stellar clump, or.
That's a good question. My guess is that you had at least a few mergers here, but I haven't looked into the merger history of this yet. You can see that some of them were like just very recently formed, so probably the brightest spots are in situ, I would say.
Yeah, so this luminosity function is mind-blowing, right? And I always thought that this band that you showed before is because ionization kills the small objects, right? So it evaporates, what evaporates the gas from small halos. So why ionization doesn't kill your dwarfs?
So at this point in the simulation volume, reionization is about halfway done.
Well, so you should have half of them gone.
Sorry?
You should have half of them gone.
What do you mean half of them gone?
Well, if it's half. It's half in what sense? It's half in volume?
Oh, yeah. So the volume is probably about halfway reionized. So the UV background in Bonfire is consistent with Planck 2018. So yeah, it's like the midpoint of reionization was around redshift 8.
So you're saying that if you go to redshift 6, it will fall down.
Probably, yeah. So I don't think I have the evolution of the UV luminosity function here, but it does, like, already it's kind of shallowing out by this point, and so yeah, you would expect it to get more shallow on the faint end. You expect it to kind of it's already, this is all, I'm not plotting any observations yet because it's also pretty striking that this is much shallower than like the extrapolations from the very high redshift galaxies right now, yeah.
So very, very nice results. So I was curious to know if you have a physical explanation why you don't expect a stellar mass dependent or UV luminosity dependent shift between the reconstructed UV luminosity function from local relics. I mean, if this works as disruption of these accreted satellites, you may expect stellar mass dependence somehow.
Yeah, and so Pratik has done, this is from his published work, so this is just with the stellar mass function. And so he's done some tests just looking at like how does this ratio of what you can recover evolve at different redshifts. And so it's not completely flat here, like there is some variation, and you do see that, especially at the high mass end, you do see that there is some variation, so it's not completely flat. And I think that kind of makes sense for what you would expect for like the merger history here, maybe the fact that Milky Way has had a major merger with an LMC size thing, I think around redshift 10 or so, something like that. So you might expect that maybe it's a little bit more difficult to recover that at the high mass end, or a little bit more uncertain for sure. But I think part of the limitations of this, so this is using like a suite of zoom-in simulations. There aren't that many massive satellite galaxies in these zoom-in simulations. And so it's just kind of statistically limited on this end as well.
Any more questions? Alex.
Go ahead, Alex.
Okay, so the local group is great, but if I just restricted the Milky Way, do you know how far down in like in UV mass, sorry, in UV luminosity, the peel off would go? Like how low mass do I have to go before just the proto Milky Way is representative?
Yeah, I don't know off the top of my head. So yeah, like I said, this is really like the results I'm showing so far, like the selection of what a proto Milky Way is, like this is first order, right? You could do a lot more here and do a lot better at selecting these, and I think it would be super interesting to see exactly how the proto environment that you're picking out affects that, yeah.
All right, let's thank Jenna again.